Hello, everybody. Good morning, good evening. This is John Morgan. I'm the marketing manager at Ametek TMC, and welcome to our webinar, Nanopositioning and Vibration Mitigation Technologies for Advanced Microscopy Applications. We have two presenters today. First is Mike Georgalis, who is National Sales Manager for TMC. So Mike will be talking about how we use piezos to mitigate vibration for advanced microscopy. And then our second presenter will be Brian Connolly, who is the Midwest Sales Manager for Physik Instrumente, which is one of our key suppliers of piezos. We'd love to get questions, so we'll take questions at the end. We'll leave 10 or 15 minutes at the end to address questions. Please click on the panel on the right and submit your questions. So without further ado, I'll turn it over to Mike.
Thanks, John. Good morning, good evening, good afternoon. I'm here to talk today about the use of technologies for advanced technology or advanced microscopy applications. And after I speak a little bit about this application of piezoelectrics, we'll flip over to Brian, who's going to talk a little bit more in depth about piezo components and other applications, and a little bit more behind the technology behind piezoelectrics. So to start with, we'll start with an application, which is a product we make at TMC, vibration cancellation systems that use piezoelectrics for vibration cancellation. And I'll talk about why they're so good at that, at performing that function. Today's going to be a little bit of a crash course. We're splitting the webinar between the piezoelectrics with PI and Brian and myself with the vibration cancellation. So I'm going to keep things at a very, very high level, try to keep things concise. I think if there's questions, or if you guys would like to do a more in-depth dive into this type of technology, you can always contact us at TMC separately, and we have lots of other content and webinars that we've done on this topic. It's a pretty robust and complex topic, using piezos in floor vibration cancellation. So today we'll be talking about 5 key things. We're going to talk about advanced microscopy. So these are the types of applications which are considered sensitive enough from a floor vibration perspective to warrant the high performance that is afforded by using piezoelectric actuators in the vibration cancellation systems. We're going to talk about sources of floor vibration. So a little quick 101 on where does this floor vibration come from and why is it a problem? And then we're going to be talking about active vibration isolation. We're going to focus on specifically system architectures and different ways that you can detect and cancel out floor vibration using active vibration cancellation systems. And then we're going to go do a couple examples. These will be just simply photos of showing before and after when we've had a vibration problem in a microscope image, for example, and the result of solving that vibration problem. So we're going to talk a little bit about what the problems we're trying to solve here and the results. And then we're going to be, after a brief conclusion, we'll let Brian go and talk a little bit more about piezos in depth. So we use a term that's very broad. It's called advanced microscopy. And when we're talking about advanced microscopy, we're talking about a wide range of ultra precision instruments. There's a lot that are commercially available. Companies like Thermo Fisher and Applied Materials and Carl Zeiss and Tescan and Hitachi. These are all making these scanning electron microscopes or transmission electron microscopes or focused ion beam microscopes. But we're also talking about other types of microscopy like multiphoton and confocal microscopy. We're also talking about semiconductor manufacturing and wafer inspection tools. So optical metrology is a pretty common one. We're using interferometry and things like that. We also dabble in the photonics business, where you've got some of your long path femtosecond lasers, like the petawatt lasers and holography and virtual reality. Even making precision optics for virtual reality is something that could be sensitive enough to warrant vibration cancellation systems that provide the level of performance that we're going to be talking about in a couple slides. And when we're talking about these microscopy and this microscopy field, we're looking at extremely tiny features. And one of the good examples of how small features we're trying to resolve here when we're talking about advanced microscopy, you're talking about microns or micrometers, and think about a human hair. When you're talking about features that are microns, you can take a human hair, cut it lengthwise about 10 times, and then you start at the micro level. We start getting to the nano level, so you start talking to folks like TSMC that are looking at 3 nanometer nodes on their microchips, or you're talking to cryo-electron microscopists who are looking at, for example, the COVID-19 virus and the tendrils that it uses to bond to a cell. You're talking about things that are on the nano level. And at the nano level, we're taking a human hair and we're sectioning it 10,000 times. Another good example is, say you're on a satellite and you want to find an ant on an island of Manhattan. This is the sort of resolution that you're looking at. We're talking about miles above the Earth's surface, looking for something the size of an ant. So you can see at these scales and at these distances, vibration. Somebody walks by in the lab, or somebody bumps your instrument. This type of thing can cause all sorts of problems in the image, and it's a challenge that advanced microscopists are always dealing with. And what's so interesting about advanced microscopy is the places where they tend to do advanced microscopy tend to be very noisy places. So you have universities in town centers and in city centers where you have lots of noise from traffic and from people walking around in the building. You have elevator shafts going up and down the building, which vibrate the building. There's pumps and motors and HVAC systems. There's construction nearby. We even see things called seismic noise, not seismic noise like earthquakes, which are a whole completely separate problem for advanced microscopy. We're talking about geological phenomena, which an interesting one is the microseismic peak. And if you imagine yourself sitting by the seaside and you've got the waves crashing on the shore, well, you can count those waves and you can count one every second and a half or so, give or take. And that's roughly 0.3 hertz. So it's a very, very low frequency waves crashing on the shore. And you can actually, if you have a geophone sensitive enough, you can place this on the ground anywhere in the world and find a 0.3 hertz vibration due to the sum of all the waves crashing on all the shores in the world. And that's called the microseismic peak. And we have customers that have instruments that are sensitive enough that this 0.3 hertz from waves crashing miles away is causing them problems. Solar vibration is everywhere. It's in cities. It's in the middle of a field. In a factory isolated out of any other sort of external sources, because that factory, like a semiconductor manufacturing facility, is going to be filled with instruments. So you have your external sources, you have your internal sources, and you have all sorts of input into the floor, which is causing floor vibration. It's most critical for microscopy in the 1 to 50 hertz range. Another factor is the fact that it exists in 6 degrees of freedom and it exists horizontally and vertically. So we're not talking about guitar strings here necessarily, and we're not talking about one-dimensional vibration. We're talking about a floor with standing waves on it that, if you could look closely enough, it almost might look like raindrops are falling on it. You've got rings and nodes and all these sorts of interferences and funny shapes that are always happening in the floor. And this is due to all the natural resonant frequencies that might be in the floor. So imagine you have somebody walking up and down. That's going to excite a vertical frequency. But imagine you're in a tall building and you're on the 11th floor. Well, that building's going to want to sway in the wind. And you might not see that swaying in the floor, but you're going to feel that swaying of the whole building. And what's so interesting about a swaying building is that a horizontal motion can sometimes be is often translated into a vertical motion, because you're dealing with rigid connections where the floors meet the walls at a right angle. And so you have this torque that's placed on that joint, which then causes a floor to then bounce up and down, which we call the drumhead effect. So that's very, very interesting, because you could be at the ground floor of a facility with a very, very thick slab, but the building might be swaying back and forth, and that could actually cause a vertical vibration in the ground floor. And it can vary all over the place. You can place your accelerometer or your geophone at one place on the floor, and you might be on a node. And you might say, okay, this floor is very, very, very quiet. I have no problem, because you're at a node, which is maybe a location where the vibration is changing from a positive displacement to a negative displacement. Or you could be at the top of a node, where you might see an extremely high level of vibration. So when you're out there measuring floors, you kind of want to place your accelerometer in a few different places to find the high points of these standing waves, because when you put a tool down there, you're going to be dealing with probably several different levels of vibration, even down to a few inches in different places. And that's also important, because you need to be thinking in 6 degrees of freedom, because an instrument, a microscope placed on a floor, is going to be riding these standing waves, and it's going to be tilting, it's going to be swaying, it's going to be rolling and rocking in 6 degrees of freedom. So that's all very, very, very important when selecting vibration cancellation systems and considering for measuring floor vibration. Another challenge you find when you're looking at floor vibration is you've got to be able to distinguish between floor vibration and vibration from other sources. When you take a measurement with an accelerometer, you've got acoustics and barometrics. So acoustics are people talking in the room, and they're your audible frequencies, roughly 20 hertz to 20,000 hertz. But they're also your inaudible frequencies, which are called barometrics. So when you go to very long wavelength and low frequency pressure changes in the room, we consider that a subclass of acoustics called barometrics. And something like that might be caused from maybe an elevator going up and down a shaft, which is going to move a whole lot of air through the building very quickly and cause a suction that could cause a wave and a pressure change in a room. There's other things that you're going to be watching for, like resonances in the isolation system. I'm not going to spend too much time talking about passive systems, but you have active systems and passive systems. And one of the things that you really got to look at are, you have an isolation system that might even be built into your microscope. So a lot of these scanning electron microscopes that are commercially available are going to have their own internal isolation systems. And there might be passive systems based on air. That's the most common one. And so it's a 2 hertz isolation system. You can go to a column. I wouldn't recommend it, but you can go to a column of any scanning electron microscope and start pushing on it, and you can drive it at roughly its resonant frequency of 2 hertz. We also see this type of isolation system using optical tables, where they're resonating at 2 hertz but performing very, very well at higher frequencies. Another good example of a 2 hertz resonance is your car springs. You can go to the bumper of your car and drive your car at roughly 2 hertz. And it's not going to go up and down a lot, because it's highly damped by the fluid in your shocks. But you will still have that resonant frequency, and you could push it and drive it at that resonance. Instruments themselves also generate their own noise. We see a lot of pumps and fans and things like that, and even umbilicals and cables, all part of the system that are going to generate its own noise. And a classic example of an instrument generating its own noise might be an instrument doing wafer inspection in a semiconductor manufacturing facility. Because what you're going to have is these wafers. They're going to be 300 millimeters, 200 millimeters in diameter. They're going to be silicon, and it's going to be one of the first raw materials you'll be using to make your microchips. It's going to want to travel through that instrument at very fast speeds to do whatever operations that need to be on it, usually metrology or optical metrology or interferometry. And the motion of that wafer through the instrument as it starts and stops induces a lot of vibration, which needs to settle in time for you to be able to do an accurate measurement. It's a really classic example of self-generated noise. So all of these things are all different sources, but they all require different mitigation approaches. And today we're just going to focus on floor vibration cancellation, and then we're going to focus on active vibration cancellation, and specifically the use of piezoelectrics in active vibration cancellation systems. And one of the, and here's an example, two free body diagrams. And these are free body diagrams representing two different types of vibration cancellation systems. And they're active vibration cancellation systems. And the key aspects of any active system are, one, you need three components. You need some sort of sensing device, which is usually a geophone or an accelerometer. Two, you need some sort of device that's electromechanical that will provide some sort of actuation. So that is typically going to be a force, a voice coil, like a linear motor. We also see this accomplished using pneumatic, varying the pressure in pneumatic systems. We also, and the one that we're going to focus on is, we also see the actuation provided by piezoelectric stacks. And the third component needed is some sort of feedback control system. So here's the two architectures. We call them parallel type and serial type. In a parallel type system, you have your three components. And the key thing to remember is that your force actuator is not load bearing. And most times it can't be load bearing unless it's a pneumatic force actuator. But the key is the force actuator is augmented by something that is a passive isolator. So you have a damped spring and a force actuator acting in the same plane on the payload. And the payload is going to be your instrument, or more often a platform upon which your instrument sits. And then the sensing occurs at the payload. So you have a sensor sensing whatever the payload motion is. It is a feedback system. So what it's going to want to do is try to keep the sensitive signal at zero, basically. So it's going to want to try to send a signal that's equal and out of phase to what's being sensed on the surface. And it's going to go to its voice coil motors, and it's going to say, okay, well, this is the force that we have to apply to try to make my sensors stay still. And it's usually, for very, very layman terms, it's equal and out of phase. And then the second type is a serial type system. And so what's unique about the serial type system can only be accomplished using using a force actuator that's capable of being load bearing. And that comes to us in the form of a piezoelectric stack. And the piezoelectric stack is basically a stack of it almost looks like half a roll of quarters. And it's got a very, very high resonant frequency. It's very, very stiff, and it's very, very, and it's capable of bearing high loads. So what you have here is you have an additional component that you have to do. If you want to create a serial type system, you need to somehow separate your load-bearing piezoelectric actuators from what it's supporting. So we have this inner mass in the middle here, and we place our sensor on the inner mass. That sensor does the same thing that it's doing in a parallel type system. It wants to stay at zero, and it sends a signal. It sends its signal to the feedback control system, which then tell the piezoelectrics to expand and contract and provide a corrective displacement over what's sensed, equal and out of phase. And we're using the reverse piezoelectric effect, which means we're applying a voltage to the stack. And because that stack is sensing that voltage, the ceramic crystals inside are going to expand and contract. And we're talking about orders of microns here. So 6 to 12 microns is actually kind of high displacement for what we've seen here, but that's the levels of sensitivity we're dealing with. So we've got this load-bearing stack, we've got this feedback control loop, we have it on the inner mass, and we have the passive component, which is then supporting the payload, which is, like I said before, usually a platform supporting your microscope. And what's the key difference between these two systems? And there's a lot of key differences, but I'd say it really boils down to, one, the location of the sensor, and two, the resonances that are inherent to the vibration isolation system itself. And if we look at go back to the parallel type system, we see the sensors on the payload. So one of the problems there is that the payload motion and any noise on the payload is getting pushed into the sensor, which means lots of information is coming to the sensor and then trying to get canceled out by the force actuator. It can't tell what floor vibration is. It can't tell whether or not it's trying to cancel floor vibration or payload vibration. And you might think that is a good thing. In some applications, yes, it is a good thing, like the semiconductor tool, which is trying to cancel out its own vibration. That's a really good, that can give you some very good settling times and cancel out onboard motion. But it's not great for floor vibration because you have that extra input. So all that extra input from the payload and what's going on in the payload then starts to hamper your ability to achieve performance at lower and lower and lower frequencies, because it's a question of bandwidth. The more input you have to the system, the less bandwidth that you have to be able to cancel out at lower frequencies. And so low frequencies are really important for floor vibration cancellation because those are common frequencies for building vibrations. We're talking about 1, 2, 3, 4, 5 hertz. These are all low frequencies, which are common in buildings and are also common in the isolation systems that are provided in the tools. Remember, I had mentioned before that a scanning electron microscope might have a resonating at 2 hertz pneumatic isolator. Well, you've got to consider that the sensitivity of the entire system. The other thing to consider about this is that the inherent resonances of the system, not only are there resonances on the payload that are causing problems, but there's also resonances of the spring here. And this spring, if it's a low frequency spring, which usually it is, 2 hertz to 10 hertz, it's going to have a resonant peak that's going to be introducing more and more energy into your sensor and therefore further reduce the amount of bandwidth you have for low frequency cancellation. But in the serial type system, you have all stiff components. We're not using low frequency passive isolators here. The inner mass here has a very, very high frequency in the thousands of hertz. And piezoelectric stacks are also very high resonant frequency systems. Furthermore, we're isolated from payload noise. So the payload might be doing all sorts of things on top, but we've got this spring here, which has a reverse effect. It's not really its purpose is not necessarily, not 100% floor vibration cancellation, but it's also providing isolation from payload noise to the sensor. So what you have here is you have a system with a lot of high resonant frequencies. You have no payload noise going into the system. And that in turn gives you the ability to have a lot of free bandwidth. It's a much more pure bandwidth that's going to allow you to provide cancellation at low frequencies, these sub 5 hertz and 2 hertz and 1 hertz frequencies. So what's the difference in performance? Well, the difference in performance when we talk about vibration cancellation systems is very, very clear. And we talk in terms of transmissibility. When we look at a transmissibility curve, the first thing we care about is unity. So the number 1 here, where everything over 1 is amplification and everything below 1 is isolation. And then the next thing we start to look at is, well, what are the frequencies at which we provide isolation? And we're looking at logarithmic scales here. So here's 1 hertz, here's 0.1 hertz, here's 10 hertz. And at 2 hertz, we go up and we start seeing, well, which is the line that is lower at 2 hertz? And you have your serial type line, the blue line. So here we're at 90% isolation at 2 hertz, which is roughly 10 times reduction. And whereas what's achievable at 2 hertz with a parallel type system is far, far less, if any. So we're looking at maybe 30%, 20 or 30% cancellation. So not nearly enough as much cancellation available, and that's because of all the internal system resonances. We don't actually start to see that with a parallel type system until very high frequencies, 5 or 6 or 7 hertz. So the advantage is clear. If you're looking for that low frequency floor vibration cancellation, you want to be using a serial type system because its architecture and the piezoelectrics used inside it are going to allow you to get much more cancellation at lower frequencies, even down at 1 hertz, we're seeing cancellation of roughly 50%, whereas we're amplifying at 1 hertz with the parallel type system. Now there is an amplification that sometimes shows up in serial type systems, but what's interesting about that amplification is that it's due to the control loops, and it manifests itself in a drift that is very, very low frequency, and at that frequency, most things are behaving as a rigid body. So that drift is usually not manifested in most microscope images. You'd have to be going to some very, very specific and very, very unusual systems, highly sensitive systems, to actually experience that drift. We rarely see it as a problem in microscopy. But the 1 hertz resonance here, that's close enough to the resonant frequencies of internal isolators that it usually is a problem. And I'll talk about that as we go through some of our examples. Here's a really good example. So here's the problem we're trying to solve. We have this scanning electron image on the Thermo Fisher SEM. They're fairly coarse. These are roughly 100 nanometer features, but very, very characteristic are these ripples around the edges. Once you put this on an active vibration cancellation system, a serial type piezo-based active system, there's a you can see that those waves in the image are gone. Another example on this Hitachi SEM shows a similar thing. We zoom into this portion of the image. Now we're trying to look at like 10 nanometer features. Look at all these problems with forward vibration over here. You put this on a serial type piezo-based system, and you get rid of those ridges. Here's a cryo TEM that is a really good example. So these guys are not only looking at extremely small features, it takes them a long time to do their measurement. So they might run a system for a cryo-electron microscopy. It might have to take a week to get one image, one 3D rendering of some sort of macro biological particle, structural biological particle. And I don't have images from this one, but what I do have are the transfer functions. And this is very, very indicative of the type of performance that you'd want to see from a piezoelectric active cancellation system. And when we look at these, we see the floor vibration being measured. Here's 2 hertz. And we see floor vibration in Gs. So this is the acceleration of gravity. So we would say 10 micro Gs at roughly 2 hertz. And we see that jump down to roughly below 1 micro G at 2 hertz. So it's over a 10 times improvement at this very, very low frequency. And the performance between the measurements on the floor and the measurement on the platform top is by an independent sensor is obvious. We see the similar performance in a really good separation between the floor and what's measured on the platform top and the horizontal as well. And here's a final example where this was done at Thermo Fisher. They wrote a blog about it. You guys can link to that blog here. But they were also experiencing over in Hillsboro, Intel, which is always doing, they're a big fab there. They're always doing expansions and construction. They were having trouble with this tool beam due to floor vibration. They were trying a parallel type system. It wasn't providing enough cancellation. So they switched to a serial type piezo-based system, and they were able to get this sample image from looking like this to looking like this. So in conclusion, there's a lot of factors that contribute to floor vibration. It can be mitigated through the use of active systems, but you got to be careful which type of active system you use to solve what type of problem. And the most important thing is the world's most sensitive microscopes, like the TEMs and the SEMs and the FIBs out there, they require that 2 hertz isolation that can only be supported by Stasis, which is our brand name, of the piezoelectric serial type active systems, which are resistant to payload noise and they're compatible with the internal isolators of the microscope. That's the end of my presentation, and I'll stop and I'll turn it over to Brian, to John, who will turn it over to Brian.
Thanks, Mike. That was great. All right, so let's just switch over and make Brian the presenter, and we'll learn a little bit more about how piezos work and other applications.
Yeah, thanks, John. And yeah, thanks, Mike. And just want to thank the audience and TMC for inviting me to share some slides on nanopositioning and advanced microscopy techniques. So I am Brian Connolly. I'm managing the Midwest, as John said, for Physik Instrumente. And I can really appreciate TMC's technology coming from background in microscopy and spectroscopy. Noise can be problematic, so it's really nice, nice talk. So jumping in, I'll go over some of our competencies at Physik Instrumente and some design considerations when choosing motion and control technologies for nanotechnology, nanopositioning, different imaging modalities. So PI has been around for over 50 years. We continue to be a leader in piezo technology as well as precision motion and controls. And we've been involved in nanotechnology really from the beginning with advances in photonics, astronomy, microscopy, and the semiconductor fields. And all these have needed high positional precision and stability. And today we continue to serve cutting edge applications, including advances in medical devices, laser processing and performance automation. And this goes from R&D efforts and projects up to OEM and manufacturing in semiconductor and other fields. So starting out with piezo basics. So PI is really best known for piezo technology, and that's really been critical in nanotechnology. And so piezo materials, as Mike mentioned, have the special property that you can apply a voltage and have a strain. So you can essentially have a resolution that's only limited by your electronics noise. And PI manufactures many different types of piezo components, chips, discs, tubes, shear elements, benders, stacks. So we have a lot of technology available. Primary focus here is in stacks. So these are discs that have been added up and operating in a longitudinal strain mode. This is done to improve the amount of travel we can get. Typically, we're only getting about 0.1, 0.15% of our stack length in total strain. And we can increase the application space of piezos by building these into other mechanical devices, EDM cut flexures, which will lever amplify the piezo. And we can further improve the application space by building them into more advanced devices with integrated sensors and closed loop feedback controls. And one thing that we always have to keep in mind as we're using piezos and building piezo devices is, as we're increasing the travel, increasing the length, using lever amplification, we're typically reducing the resonance and stiffness. So, each application needs to be evaluated to find the, the optimal solution. So PI does build all these piezos in-house. We have lots of different formulations as well. One of the main ones is the Pigma low voltage piezo ceramic, which is a lead zirconium titanate type piezo. But it does get away from the traditional route of having polymer coated discs that are then glued together, and instead going to this method of manufacturing that creates a ceramic insulation in a monolithic actuator. And so this has really significant improvements for lifetime, also for robustness in different environments. And these were selected by NASA for the Mars rovers for this reason. So one of the primary uses of piezos in microscopy is in fast focus drives. A main reason of this is piezo operates as a frictionless element, and as well as the EDM flexure is operated in elastic mode. It's frictionless, being achieve high dynamics for very quickly scanning through a sample where you may have a spatial resolution or a depth of focus with super resolution and advanced microscopy techniques that are tens of nanometers. And so you're needing to collect many image stacks. You want to do this quickly. And these devices really enable that, whether you're inspecting a wafer in semiconductor or a tissue in a biomedical application. Recently, we've come out with some new designs that further improve the stiffness of these devices and allow really the best settling and dynamic performance on the market. Typically, as you go up to longer travel, you're losing some dynamics, but really with these new designs, we can even achieve 800 micron devices with tens of millisecond settle times to error bands that are really really small. So we're talking about nanometers here. We're talking about micro radians of off-axis error. PI has advanced controls to really maximize resolution, minimize noise in these types of technologies. So we've really been, enabling advanced microscopy for many years and involved with many research institutions like Howard Hughes and Jamelia campus. There's an example of, ISO plane setup from the early days. They're still doing this today with piezo technologies, whether it's Pi-Folks or stages. Or piezo scan mirrors for adjusting planarity of light in these setups or doing scanning. Of course, sometimes we need to extend beyond even the hundreds of microns, maybe get into the millimeters of travel. And we have a whole myriad of technologies to do that. One that I'll discuss here is a voice coil stage. So a voice coil gets away from the traditional servo and stepper lead screws and ball screws. So it's more of a frictionless platform. This usually has the drawback of not being very good for operating in a vertical orientation. But here we've introduced a magnetic counterbalance that can basically compensate for loads up to 1 kilogram. And that really allows us to then use the full dynamic performance of the stage and allows us to reach several millimeters of travel with integrated optical linear encoders. We can achieve very high precision and dynamics. So this would be good for some of the deep tissue imaging, multi-photon techniques, in neuroscience and other fields that are really trying to, build these very large images. A lot of this has been enabled by super resolution and localization techniques. And so, yeah, we want to continue to advance what can be done with the motion technologies. Here's an example of some performance from this drive. So we can clearly make very well-defined 10 nanometer steps. So this is an example of 100 nanometer kind of step and settle with very fast rise times and settle times in the 10 to 15 milliseconds. So this is, not quite as good as a piezo flexure, but really getting to be very good performance for this type of technology in travel ranges. So of course, a lot of times we want to do multi-axis positioning as well, and maybe do sample scanning in AFM, SPM, in XYZ. And we have to consider some different design, mechanical designs that we can do. And so the first thing we always think about here at PI is whether we are, going to just take simple single axis flexures and stack them or nest them, or if we're really going to do a parallel kinematic design where all the piezos are built around a single moving platform. And this is just a good example of a couple of our nanocubes where you can clearly see that there's 3 moving platforms built in. Now this one having just a single flexure that is completely parallel. And so with the parallel design, you can really compensate for any off-axis errors in a very dynamic way without any kind of accumulation errors. These designs, of course, can be more economical. So really have to look at the application and see what makes the most sense. And we have a lot of these designs really just available, including ones with open apertures or designs for AFM, increased stiffness for higher dynamics. Kind of the second thing we have to consider is what kind of sensors we're going to put in. We typically would work with capacitive sensors, which provide kind of a non-contact measurement of the motion platform, even to sub-nanometer scales. These are typically very good on stability. We can also use a piezoresistive type sensor, a strain gauge. These typically measure kind of a force in the moving platform and use that to infer the position based on the calibrations, the interferometer calibrations. These can have some advantages in terms of reduced cost if we need to integrate to a smaller device, but really for best precision and stability, capacitive sensors are the better way to go. So with these advanced microscopy techniques, depending on what kind of imaging is being done, these can take it can take a long time to generate hundreds of thousands or millions of images sometimes, and obviously you don't want a lot of drift. So in all these optomechanical setups, you're susceptible to drift from thermals and things. So parallel kinematic stages have really been used in projects at NIST in Colorado, and this has then been incorporated into other labs where we're really measuring drift and compensating it in real time here with really a direct drive, kind of the highest stiffness, highest dynamic kind of sample positioning, 3-axis stage. And the controls can get fairly complex, and PI has really, I think, outstanding world-class controls team where we can consider dynamic compensations with high bandwidth. Also often do piezo-based mirrors that can allow us to compensate laser positioning, and so to compensate drift in kind of with a steering mirror with a very precise manner. So we can also use piezos to do some longer travel. Here we build the piezo ceramic into an actual motor. There's a bunch of different flavors and varieties of these. Typically, we'll use ultrasonic piezo motors more for fast scanning, and these inertial or stick slip more for kind of step and settling. Piezo walk is really kind of the pinnacle of piezo motors, where we can get very high force and very high precision. So you can see kind of a 3-nanometer step, and this can then be done over inches. So all these kinds of motors can be used in linear rotary stages, and there's a variety of products out there. The one here is you know, what we would call a long travel stage for microscopy, for confocal microscopy, or also used in conjunction with flexures and free space setups to enable kind of a long travel with high precision, and then also a fast scan stage on top. All the piezo motor stages have the really nice feature that when they're not moving, they're self-locking. So the motors really don't have the servo jitter that you get from traditional motion technologies. The ultrasonic is really nice for scanning. We can actually tune it to, a very wide range. So we can actually do, ultra slow raster scans with good velocity constancy, which is really important in, new, in imaging techniques where cameras and detectors are so fast, we don't really want to stop the motion. We just want the images to come at very even spacing. So this is a really nice feature of using these for long travel stages and not having to worry about stitching artifacts and things. So just to conclude, here's a good example of a system that was developed at Yale and Professor Hung's at Purdue now, and really using piezo flexures. There's a flexure on the lower objective, so there's a 4-pi single molecule imaging system that really localizes 2 beams with high planarity and allows a modality that's pretty special with deformable mirrors for coherent detection. But really, on this or SEM, TM, all these advanced techniques, we want the motion to be as precise and stable as possible. There's a lot of imaging and tricks you can do with the data, but you want to start from the most noise-free and precise place possible. So we use PI line longer travel stage, flexure for scanning, and piezo walking for bringing the upper objective into place. So this is, and actually there's some stepper actuators here for adjusting the planarity too. So really this can achieve depths of Z spatial resolutions in the tens of nanometers, and you can see some very nice images from this this setup. So that's it for me. Our headquarters in the US is in Auburn, Mass. I'm in Chicagoland here. Headquarters in Germany, in Karlsruhe, our wall of patents there. And please reach out if you have any questions. Please check out our blog, a lot of good learnings there as well.
Thanks, Brian. That was great. I do, Mike, I'm going to unmute you as well. I do have a couple questions here. Again, for people who have questions, please type them in. So the first one is for Brian. For the V308 stage, how do you adjust the magnetic counterbalance in vertical application for varying payload mass?
So there's really just some small wrench. You can just adjust this. There's 2 knobs on the stage body, and you can actually adjust each one because there's some counterbalance on each side. So even if you had a different center of mass, you can even compensate for that better. And we provide some small wrench to adjust this. It's quite easy.
Okay, so something the end user can do for themselves.
The really design of this stage is for flexibility. We can bring in the limit switches. So if you're concerned about some impact of your sample or other optics, you can really reduce that travel range even So it's very nice features, very easy to put different objectives and yeah, different adapters. So it's quite nice.
Okay, and then I had another one for you. Can you upgrade my microscope, either the focus or the stage, sort of aftermarket, or do I need to go to the original equipment manufacturer?
Yeah, I mean, definitely we have drop-in stages for many inverted microscopes. When we're talking about, yeah, it really just depends on the microscope. So definitely, reach out. The Pi folks, will fit. We have, adapters for different thread types and things. That's easy one. For the stages, yeah, it really depends on the mounting, and sometimes you can just build an adapter to the dovetail, or there are some options. But reach out, get us your microscope model number, and we have a lot of good application engineers to help with that.
Okay, great. And then Mike, there's one for you. It says, I'm a microscopist, not a vibration expert. So how do I decide what vibration isolation I should use for my instrument? Where do I start?
So that's a really great question. I would say I'd say the place to, if you think you have a vibration problem, there's a couple different paths. I mean, if you're pretty certain it's a vibration problem, then you should call TMC, and what we'll do is we'll ask you what your microscope is. We'll ask you if you had any measurements for floor vibration in the area. It's also a good idea to seek the advice of the OEM. A lot of times we see the manufacturer of the microscope, because a lot of times we see an image could look like it's a vibration problem, but it might actually be something else. So the microscope manufacturer might be somebody to help you out as well if you have a vibration problem. But I would say that there's not too many, and being not a microscopist, I don't know that there's too many things that I could do to help troubleshoot a scope that might have a vibration problem. I think that you'd want to try to isolate whether or not it's a vibration problem first, and then work with TMC to figure out what a vibration solution might look like for your microscope. And it depends on what kind of scope it is. If it's a scanning electron microscope, you're going to be looking at the active cancellation systems. If it's a confocal or an optical microscope, something like that, you're more likely going to be looking at some of the passive cancellation systems.
Okay, thanks. And then I had one other for Brian about vacuum performance. I mean, how do the piezo stacks react in vacuum? Is there any outgassing to worry about? Is there any heating to worry about?
Yeah, it's definitely an application we take care of. We work with a lot of national labs, and so we've done a lot of vacuum work. We have vacuum chambers in Germany for test and metrology, so we can even provide outgassing reports. Piezo itself is inherently vacuum compatible. The outgassing would be from the small glues that connect the piezos into the stages. So for vacuum, we would use, very low outgassing glues, the same ones we would use for space applications. Other materials considerations, typically on the cabling. So depending on how sensitive, like if there's very sensitive optics in the vacuum chamber, then, typically we have to go to, a fairly, advanced cabling, like capped on peak connectors. And things like that. So yeah, we take all that into consideration when we qualify an application. So we can certainly talk about that a lot, but I'll leave it at that.
All right, thanks. It looks like that's it for questions. So just want to thank everybody for joining us, and the webinar it has been recorded, and we'll send a link to you to view the recorded webinar and to share with your colleagues. So thanks very much for joining.
Thank you.
Thanks, everybody.